Okay, now we're going to talk about some more practical digital to analog to digital conversion type stuff. Um, First thing we're going to talk about is digital to analog conversion. There's an ideal digital analog converter, and remember we kind of set it up as a pulse generator, and the height of these Dirac delta pulses are set equal to the value of x of n. And the output of this is a train of delta functions that are weighted by x of n. And then, since this has kind of a very bizarre spectrum with spectral images every multiple of the sample rate, we have to run it through a low-pass filter to get rid of all those high-frequency images. And when we take this, go through a low-pass filter, the output of the filter is nice and smooth. This ideal low-pass filter is an ideal interpolator that connects the dots in sort of an exact fashion. Okay. Now the problem is, as you are probably well aware, we can't build an ideal pulse generator, nor can we build an ideal low-pass filter. So what do we do? Well, there's a thing called a sample and hold, and these are actually used both at the input and the output, but we're going to talk about the output application. A sample and hold circuit. Let's see, here's a real basic circuit example. We're going to replace both of these, pulse generator and low-pass filter, with this thing. And you kind of have to take a little bit on faith that we can take x of n, the quantized values of x of n, which are a fixed number of bits, like 8 bits, and we can convert that into a voltage that's proportional to x of n. And then imagine, if you will, that we have a little switch that we can momentarily set the switch down and then pull it back up every capital T seconds. What that does is it charges a capacitor, and then if the switch goes up, this voltage is held for, it's depending on the size of the resistor, it's held for a long time, and depending on what we're hooking up to this thing. Well, what happens is, since it holds that voltage, this is called a sample and hold device, we get an output that looks like this. So we get a value here, a voltage that's equal to x of n, x of 0 in this case, and it holds that voltage until the next sample, and then the capacitor is recharged to the next sample value, and so on, and we end up with a stair-step like shape. So this is sort of a compromise between ideal sampling, ideal digital analog conversion, and the real world. Okay, so this is very common. It's called a first order sample and hold, and it's not terrible. It's not great, but it's not terrible, and these are used a lot. Mathematically, it's actually kind of easy to analyze. If you remember, the ideal case, we have these pulses, and we go through an ideal low-pass filter, and it connects the dots. And in the time domain, it's convolving with the impulse response. Well, suppose we have a filter. It's no longer ideal, but it has an impulse response that's a rectangle, and it's a rectangle with a width of cap t seconds. And so this is the impulse response of a filter, and we're still modeling. This is still a math model. It's a model that involves this infinite train of Dirac delta functions. But if you convolve these together, as you remember, with the sifting property, we replicate one of these rectangles every place there's a delta function. And so this is a nice stair-steppy kind of function. So it shows that this is a reasonable math model. And the reason I even bother to write that is because the impulse response is a rectangle, we all know by now that its frequency response, the Fourier transform of this, is a sinc function. Okay, so the interesting thing about this model is when we compare it to the ideal case where the low pass filter has a frequency response that looks like this, okay, that's that low pass filter. We still have an impulse train as the input. Now with this sample and hold stair-step output, we no longer have an ideal low pass filter. I'll sketch it in here as well. We have a sink function. Okay, so this is not an ideal frequency response, as you can tell, because we're not replicating the output. We got a stair-step thing, which was not what we had at the input. So we're going to have some distortion. And the distortion, as you can see, is not bad at the low frequencies, but at the high frequencies, there's a big difference between an ideal frequency response and the sink function frequency response. So we get a lot of distortion at the high frequencies. Alright, so continuing on, I've got one more thing I want to say about this, and then we'll switch topics. But if you remember, the signal to quantization noise ratio in dB was 6.02 times the number of bits plus 1.76, and that gives us a signal noise ratio in decibels. And you know, when you're first getting started, you don't really have a good feel for what decibels mean, and so let's talk about that for a bit. It's easiest to understand when we're talking about audio applications, because everybody knows what they hear and they know what good quality is and bad quality is, and the signal noise ratio tells us about quality. We obviously want high signal power as a ratio of noise power. We don't like noise power, but we do like signal power. Here's a rule of thumb that may help. If the signal noise ratio is less than 10, these results came from studies of the phone company. That's generally thought to be unacceptable, pretty bad. Between 10 and 20, it's poor or fair. You know, it's not good, but it's sort of okay. From 20 to 30 dB, we're talking about pretty good quality. And above 30 dB signal to noise ratio, you can almost not, in fact, I can't detect any noise. The signal power is so much stronger than the noise that you almost can't detect any issues at all. And then above 40, I mean, it's just undetectable. So that's kind of the rule. So kind of keep that in mind. We talked about a CD player. They use 16 bits of in their analog to digital converter, and that gives them 96 dB of signal noise ratio. That is very, very good. But always keep in mind that this assumes that the sine wave, the input signal, is at full scale. Okay, that's a big assumption. It means that you've adjusted the input signal so that it goes from Vmin to Vmax. In other words, it's almost oversaturating the input. Most signals, like if you think about music, they may be loud for a while, but then there may be quiet places where somebody is singing quietly, or a little violin is playing in the background. And so in those regions, the signal power drops well below this assumed input value. And so we're talking now about dynamic range. And in these cases, the actual signal to quantization noise ratio can drop quite a ways down. Hopefully not below a threshold where we can actually hear any kind of quantization noise. Also keep in mind that what the meaning of 0 dB means. Remember, when we measure decibels, it's 10 times the base 10 log of the ratio of signal to noise power. If this is equal to 0, that implies that the thing in the logarithm is equal to 1. So signal power and noise power are the same. So that's the meaning of 0 dB. All right, I'm going to pause for a second.